Welcome to Hess's law of heat summation. Hess's law is based on the fact that we can break up a reaction into smaller steps. Say we have a reaction from A to C. Well, if we can find a reaction that goes from A to B and then B to C, we can treat these as steps that contribute to the overall reaction of A to C. And Hess's law is basically going to let us use the delta H for the A to B reaction and the delta H for the B to C reaction to figure out the overall delta H for this A to C reaction. So we're using the steps to figure out something about the whole reaction. More formally, Hess's law says that the overall change in enthalpy, the delta H of a reaction, is equal to the sum of the delta H's, the changes in enthalpy, for the steps of that reaction. And this is going to be useful for two reasons. The first is that there exists an infinite number of possible reactions, and it wouldn't make sense to try and just catalog the change in enthalpy for every possibility. Instead, we can just identify a few common steps, determine their changes in enthalpy, and then use them to figure out more complicated reactions. The second reason is that some reactions are difficult or impossible to measure directly. And we're actually going to use Hess's law to figure out the change in enthalpy of one of these reactions that's difficult, or actually this one's impossible to measure directly. And the reaction we're going to look at is the combustion of carbon to form carbon monoxide. Now, why is this reaction impossible to measure directly? Well, if you took molar quantities, so 1 mole of carbon, and you took half a mole of oxygen, just like the balance equation says, you would not get 1 mole of carbon monoxide. Instead, you would get a mixture of carbon dioxide and carbon monoxide. This may look familiar to you as the products of incomplete combustion. Some of the carbon will combust completely to give carbon dioxide, whereas carbon monoxide is a product of incomplete combustion, so it doesn't ever come by itself. This CO2 here is sort of a side product that we want to ignore but we can't get rid of. So there's no way to directly measure the heat associated with the formation of this carbon monoxide amount. But we can use Hess's law to figure out what the heat of reaction is for this equation. So to do that, we're going to need two steps that could be combined to make this overall reaction. Our first reaction is going to show the complete combustion of carbon. So we have carbon combining with oxygen gas to form carbon dioxide. This reaction has a delta H of negative 393.5 kilojoules. The second reaction that'll give us some more information is what happens when you completely combust carbon monoxide, so here carbon monoxide is a reactant, combusted with oxygen to form carbon dioxide gas. And the delta H for this reaction is negative 283 kilojoules. Now these two reactions don't really look like steps for this original reaction. And they're not really clear steps in the sense that A to B and B to C gives you A to C. It doesn't really work like that. But what we can do, and the trick to this whole thing, is that we can manipulate these equations algebraically. And to do that manipulation, I'm going to start by flipping reaction 2. I'm going to flip this around. So instead of having carbon monoxide reacting with oxygen gas to form carbon dioxide, I'm going to write this as the opposite. I'm going to show this as the decomposition of carbon dioxide gas into carbon monoxide gas and oxygen gas. Now the original reaction was exothermic. If I do the opposite of that reaction, it's going to be endothermic. So the delta H becomes positive 283 kilojoules. Now Hess's law lets us add reaction 1 and this new reaction 2, and if we add those reactions together, we're also going to be adding their delta H's together. So we're going to add reaction 1 with the new reaction 2, so these two things, we're going to add them together. And we're also going to add their delta H's together. These two delta H's we're going to add together. And let's see what happens when we do that. First, I'm going to rewrite these equations so that they look a little bit cleaner. So here's reaction 1 and reaction 2 rewritten. I've dropped out the state symbols just to clean it up a little bit and make it easier to see what we're actually manipulating. I'm going to put a big plus sign here because I'm going to add together all of these things. And we're going to treat this arrow, the reaction arrow, as an equal sign. Now before I add these two reactions together, if any compound appears the same on each side of the reaction, such as the carbon dioxide on the product side for this, and the carbon dioxide on the reactant side for the second reaction, they appear the same in each equation but on opposite sides. So that's going to let me cancel those out completely. Now I just bring down the rest. I'm going to add up everything on the reactant side for each equation, and so the only things left over here are carbon and oxygen. Then I'm going to add up everything on the product side, which is only carbon monoxide and again oxygen gas. Now I'm essentially going to combine like terms. I have an oxygen on the product side and an oxygen on the reactant side. I don't want them on both sides. So the way to get rid of that is that I'm going to subtract this half oxygen from this side, which will give me only half an oxygen left on this side. Because I had one, I subtracted the half, so now I have half an oxygen left on this side. Now I also need to add up these delta H's. So negative 393.5 plus 283 kilojoules is going to give me a delta H for the overall reaction that is showing up on the bottom here of negative 110.5 kilojoules. And now if I look at the overall reaction I have down here, I have carbon plus 1/2 oxygen yields carbon monoxide. And that's the same as this original equation I was looking for. So the delta H for the original equation I just figured out using Hess's law. And that's negative 110.5 kilojoules. Now the same principles that allow us to use Hess's law are going to let us use the standard heat of formation to do the same process. Now remember, standard heat of formation is for a particular compound. And there are 3 particular compounds in this example equation. So there's a way to use the standard heats of formation for NO, O2, and NO2 to find the overall standard heat of reaction for this reaction. And that looks like this. The standard heat of reaction is equal to the standard heats of formation of all the products minus the standard heats of formation of all the reactants. So I'm going to need to know the standard heats of formation for all the reactants in the products. And that information can usually be found in a table of thermochemical information, such as this one. So we're going to use the values in this table to help us figure out the overall delta H, the overall heat of reaction for this reaction. Let's start by getting the values for each of these compounds from the table. The first reactant, NO gas, has a standard heat of formation of 90.37 kilojoules. I'm going to multiply that by 2 because there are 2 NO molecules on the reactant side. Next, I'm going to look at oxygen. Now, oxygen is an element in its most stable state, and any element in its stable state at the standard condition is going to be 0. So oxygen is just a 0. Next, I'm going to look up NO2, which has a standard heat of formation of 33.85 kilojoules. And I'm also going to multiply this by 2 because I have 2 of them. So the total for the nitrogen monoxide gas is going to be 180.74 kilojoules. Oxygen is still 0. And the total for the NO2 gas is going to be 67.7 kilojoules. So now I'm going to use this equation and this information to find out the overall heat of reaction for this reaction. So the standard heat of reaction is equal to the total heats of formation for the products, which is, in this case, only 67.7, minus the total heats of formation for all the reactants, which in this case is going to be 180.74. If I now solve that, I'll see that the overall standard heat of reaction is negative 113.04 kilojoules. And that's how I can use the standard heats of formation for all the compounds in the equation to find the overall heat of reaction. And this method is based on the same principles that Hess's law is based on, because I'm essentially saying that the steps are for each of the components of the reaction: the formation of NO, the formation of O2, and the formation of NO2. I'm treating each of those formation reactions as steps to put together to get this overall equation. That wraps up our lesson on Hess's law of heat summation. Write down any questions you have in your notes and bring them with you to class.